Welcome to a video on quadratic functions. On example 1, we'll be solving quadratic equations over the complex numbers, which includes non-real solutions as well. To solve a quadratic equations, recall there are several methods. Refer to our notes from section 3.2 and review them. The first step is to write the equation in standard form. That is, move the 1 over to the left-hand side. This is going to give us 8x squared plus 7x minus 1 is equal to 0. We call this the standard form of a quadratic equation. Now, if the equation is factorable, go ahead and factor. If it's not factorable, then we'll consider other methods. Here we have a leading coefficient of 8 and a constant term of -1. To determine if a quadratic equation is factorable, we start with the product of a and c, which is 8 and -1. This gives us -8. And then we need to think of two factors that sum to the linear coefficient, which is 7. So we can go with a -1 and a +8. The product, multiplying them, that is -8, but the sum, adding them together, will give us a +7, which is the linear coefficient of this statement. So this means the equation is factorable. From here, we can replace the linear term 7x with a -1x and a +8x, giving us a 4-term polynomial on the left, and then approach that factoring by grouping, or we can just factor by guess and check now that we know that it's factorable. So the guess and check approach is basically what I call the unfoil method. So basically, I want to think of two factors that multiply to 8x squared. So start with 8x and 1x. And then for the last term of these binomials, we want to multiply two numbers together to get a -1. So we can go with -1 and +1. But now we need to check to see if the inside from FOIL and the outside from FOIL together will give us the +7x, which makes up the middle term of the quadratic equation. So if we evaluate the inside from FOIL, we get a -1x, and then the outer terms, multiplying them, we get a +8x. Hence, adding them together, which are considered like terms, that will give us 7x. So this works out, and again, this is just guess and check, which happens to work out on the first try. Alternatively, if you don't like this approach, you can take this quadratic expression, 8x squared, replace the linear term with these coefficients here, the factors of AC that sum to 7x there. So those factors were -1 and 8. So we're going to make a substitution for 7x as -1x and a +8x. As you can see there, that makes up the middle term of the statement. And now followed by the original constant term, which is -1, and then 0. So this is just a substitution for the linear term to turn this into a 4-term polynomial on the left. From here, usually when we're given 4 terms, we can factor by grouping. So based on the first group, which basically consists of the first 2 terms written there, we're going to take out the greatest common factor, which is 1x, leaving us with 8x minus 1. And then on the next group, which consists of the last 2 terms of the expression of this statement here, and so taking out its GCF, which is just a 1, we're left with 8x minus 1, and then complete the statement. Now notice what's in parentheses are the same. So now, based on these 2 terms, there's a common factor of 8x minus 1. So we'll go ahead and factor that out. Hence, what's left on the first term is 1x, and what's left on the second term is a +1. Now, this is the systematic approach to factoring if the equation is factorable. As you can see, these two factors are identical to these two right here using the unfoil method. So from here, we're going to use the zero property of equality, set each factor to 0, and solve, giving us on the first linear factor there a solution of 1/8, and then for the second one, a solution of -1. So those are the solutions to letter A of problem 1. Now let's consider part B. For part B, again, the first step is to write the equation in standard form. To do that, we're going to subtract 8 to both sides, making the constant term of 5 now. And now we can try to approach this using the factoring method again, if it's factorable. So we'll verify if it is, start with the product of AC, 4 times 5, which is 20. And now think of factors of 20 that sum to -3. So as you can see here, no factors of 20 will give us a sum of -3. Let's just list a few of the factors of 20 out. So we can start with 1 and 20, or -1 and -20, 2 and 10, right, or -2 and -10. Now, in order to get a sum that's a negative value, both these factors must be negative, because two negatives give us a positive product, but the sum of two negative numbers is going to give us a negative value. So our next pair would be -4 and -5. But again, the sum of these factors will never give us -3. And therefore, this equation is non-factorable. So if it's not factorable, we turn to either completing the square or using the quadratic formula. For this problem, I'm going to use the quadratic formula. So m equals, formula states the solution to a quadratic equation is -b plus or minus the square root of b squared minus 4ac all over 2a. So here's our leading coefficient, 4, which is a, and our linear coefficient, -3, is b. And then the constant here is 5. Again, this has to be written in standard form. So I should have gone with this statement rather than the original statement. So substituting in these A, B, C values, so we have negative of -3 plus or minus square root of the square of -3 minus 4 times A is 4, times C, which is 5, all over 2 times the value A, which is 4. So M here, simplifying it, is +3 plus or minus the square root of 9 minus, here we have a negative times a positive times a positive. So it's going to be a negative product. 4 times 4 is 16, times 5, 80, and then all over the number 8. So m equals 3 plus or minus the square root of -71, -80, and 9 there is -71, all over the number 8. So simplifying the radican, we get 3 plus or minus square root of -71. Remember, the square root of a -1 is the imaginary unit I. So we can view -71 as -1 times 71. So taking the square root of that -1 gives us the imaginary unit, and then the square root of 71 stays as is, all over 8. So this is the non-real solutions of the value m.